Good afternoon, everyone. My name is Tujin Ki, and my group members are Lau Jingxuan, Wu Jieyang, Tan Junhao, Tan Yonghan, and Xie Jing. Today, we will be talking about an analysis of marine alternative fuel for shipping decarbonizations, technologies, applications, and challenges. These articles were selected for this assignment because it provides a timely, systematic, and a holistic review of a critical global challenge, decarbonizing the maritime shipping industry. Unlike other articles focused on a single fuel type, this paper offers a comparative analysis of all major alternative marine fuel, evaluating them against technical, economic, and environmental criteria. Its comprehensive nature makes it an excellent foundational source for understanding the complex landscape of options available for transitioning away from conventional fossil fuels like heavy fuel oil and marine gas oil. The structured methodology and clear presentations of challenges and future directions provide a solid basis for critical analysis and discussion. The aim of this assignment is to synthesize and critically engage with the key findings of the selected articles. It seeks to understand the research problems of maritime decarbonization and the role of alternative fuel, analyze the methodology used to compare different fuel options, summarize and interpret the main findings regarding the viability of various fuels, evaluate the recommendations and conclusions presented by the authors, formulates an informed perspective on the future challenges and opportunities in this field based on the articles inside. Next, which is the research problem. The central research problem addressed by the article is the urgent need to decarbonize the global shipping industry to mitigate its significant contributions to climate change and air pollution. The International Maritime Organization has set stringent target to reduce greenhouse gas emissions from ships by at least 50% by 2050 compared to 2008 levels. The core problem is that conventional marine fuel are major emitters of carbon dioxide, sulfur oxide, nitrogen oxide, and particulate matter. Therefore, identifying and adopting viable, sustainable, and scalable alternative marine fuel is a monumental technological and economic challenge. The article systematically investigate which alternative fuel can meet this challenge by evaluating their readiness, benefit, and drawback. Now, I will pass it to Wenjing.
Good day, Ms. Lee. Now I'll be explaining the research methodology used in this research. The authors adopted a systematic literature review combined with a comparative multi-criteria analysis to evaluate four alternative marine fuels, which is LNG, methanol, hydrogen, and ammonia. First, the systematic literature review. Data was collected from Science Direct, Springerling, MO reports, and IEA Energy Outlooks. The review focused on studies published between year 2020 and 2025, selecting over 120 peer-reviewed papers and technical reports on technology readiness, emission reduction potential, and economic feasibility. Second, the evaluation criteria. The fields were compared across 5 dimensions: technical maturity, engine compatibility and bunkering infrastructure, energy density, storage needs and voyage range, emission performance, carbon dioxide, nitrogen oxide, sulfur oxide, and methane slip, economic feasibility, fuel price and retrofitting costs. And then the last one, safety and regulatory compliance, toxicity and IMO standards. Third, the study applied a well-to-wake life cycle assessment. This framework accounts for emissions from fuel production, transport, storage, and combustion, ensuring a holistic environmental comparison. Fourth, the multi-criteria analysis. A weighted scoring system was applied. Environmental performance 40%, economic feasibility 30%, technical readiness 20%, safety and regulation 10%. This structured approach allowed the authors to assess trade-off between short-term deployability and long-term sustainability. Finally, the methodology was validated using real-world case studies, including CMA CGM's LNG power vessels, Stena Germanica's methanol ferry retrofit, and the EU flagship hydrogen ferry project. These examples strengthen the credibility of the findings. However, the methodology also has limitations, as it relies heavily on secondary data and model cost projections, especially for hydrogen and ammonia. Future research should involve pilot-scale demonstrations and operational data to improve accuracy. In summary, this methodology combines systematic literature analysis, life cycle modeling, and case study validation, providing a robust framework to assess marine fuel options under the IMO 2050 net zero targets.
Good day, Miss. Now I'd like to present the main findings. This study provides a comprehensive analysis of LNG, methanol, hydrogens, and ammonias as alternative marine fuels, highlighting that each fuel has significant potential to reduce greenhouse gas emissions in the shipping industries, while also having its own advantage and disadvantage. First, LNG technology has achieved commercial maturities and is an effective short to medium-term solution, but it is constrained by maintenance slips and infrastructure gaps. However, it is considered a transition field because it still emits carbon dioxide, despite at lower levels than traditional marine fuels. Second, methanol fuels is liquid at room temperatures, making storage and handling simpler compared to LNG. It is also a renewable energy source with the potential to achieve carbon neutrality. Additionally, its infrastructure is currently under development and converting energy to methanol fuels is relatively straightforward. Third, hydrogen fuel emits zero carbon when used, producing only water when used in fuel cells or combustions. It can be produced through renewable electricity, such as green hydrogen. However, storage poses challenges due to its low volumetric energy densities requiring high pressure tanks for storage. Finally, ammonia fuel is a carbon-free fuel synthesized from green hydrogen and nitrogen. Ammonia's toxicity and corrosiveness requires stringent safety measures and specialized fuel systems, resulting in limited infrastructure for ammonia fuel. This is all for my part. Next, I will pass to Yong Heng. Thank you.
Good day, Ms. Lee. Now, let us move to the interpretation of the findings. The article evaluates four main alternative marine fuels: liquefied natural gas (LNG), methanol, hydrogen, and ammonia, as they mentioned before, and compares them in terms of technical maturity, emission reduction, cost, and safety. While the article provides a comprehensive comprehension, I will highlight several points where we agree and disagree, supported by the latest evidence. First, LNG. The authors present LNG as the most suitable transition fuel, citing its maturity and its ability to reduce carbon dioxide emission by around 20 to 30% and nitrogen oxides emission by over 80%. We agree with its short-term advantage, but recent data indicates that LNG climate benefits are overestimated due to a methane slip. The International Council on Clean Transportation found that the real-world methane emission from LNG fuel ships are average 6.4%, nearly double the assumption used by IMO models. Since methane have 80 times the warning potential of carbon dioxide over 20 years, this undermines LNG role as a long-term climate solution. Second, methanol. The study highlights methanol as a promising low-carbon option due to its ease of storage and compatibility with existing fuel infrastructure. We fully support this conclusion, especially with the growing adoption of green methanol. The clean energy wires demonstrate that green methanol can achieve up to 96% of life cycle emission reduction compared to a heavy fuel oil. This makes methanol a highly deployable medium-term solution, particularly for retrofitting existing fleets. Third, hydrogen. The author suggests that hydrogen is a long-term solution because its storage and infrastructure challenge limit immediate adoption. However, the recent development indicates that hydrogen may become available sooner than expected. In 2024, the Sea Change motor vessel becoming the first world commercially operating hydrogen fuel cell ship in San Francisco Bay, powered by a 360 kilowatt class fuel cell and carry out to 75 passengers. This successful demonstration showed that hydrogen can already be implemented in short-range shipping, contradicting the assumption that it's only relevant in the distant future. Finally, ammonia. The authors emphasize ammonia high energy density and zero carbon dioxide emission potential, but highlights concern over the toxicity and safety. We agree with its long-term potential and adds further evidence. In 2024, Emogi retrofitted a tugboat to run entirely on ammonia, making it the world's first ammonia power vessel. However, the challenge remains. Jaslyn reports that ammonia power vessel currently cost 2 to 4 times more than a conventional vessel, and only 27 dual-fuel ammonia ships has been ordered globally, compared to a 641 LNG and 340 methanol vessel. This shows that while ammonia holds promise, significant cost reduction and safety regulations are needed before widespread adoption.
Hi, Miss. My name is Dandratha. I'm going to continue with the recommendation parts. The decarbonization of international transport, particularly the maritime sector, require a holistic strategy that involves governments, port authorities, and industrial actors. The transition toward alternative fuels such as LNG, methanol, ammonia, and hydrogen is central to this process. The first is the government and international regulators. Government and international regulatory bodies such as the IMO should establish long-term policy framework to accelerate the adoption of alternative fuel. A global carbon levy of market-based measure can incentivize early adoption of low-carbon fuels while generating revenue to reinvest in research and infrastructure development. To avoid the fragmentation, regulators must harmonize standards for bunkering and safety procedure across jurisdictions, especially for high-risk fuels such as ammonia and hydrogen. Moreover, policy must include mechanisms to support the developing countries so that the benefits of decarbonization are equitably distributed worldwide. The next is the port authorities. The port authorities play a crucial role in enabling the uptake of green fuel. They should invest in multi-fuel bunkering infrastructure that can accommodate LNG, methanol, ammonia, and hydrogen simultaneously, thereby reducing the risk of technological lock-in. In addition, ports should adopt advanced safety monitoring systems such as AI-driven leak detection and IoT-based operation control to manage risks associated with volatile green fuel. Collaborative initiatives like Green Shipping Corridor, which designs specific trade routes for zero-carbon vessels, should also be expanded to demonstrate the feasibility of large-scale decarbonized shipping. The third point is the shipping companies, shippers, and logistics firms. The shipping industry and its customers, shipper, and logistic provider must work together to accelerate decarbonization. Shipping companies should adopt phased fleet transition strategy with dual-fuel vessels providing flexibility during the energy transition. For example, Mars has already commissioned methanol power container ship as part of its long-term decarbonization plan. However, shipping company cannot bear the cost of transition alone. Shippers and cargo owners must contribute by incorporating emission criteria into procurement decision and agreeing to green premium in contract, where they cover part of the cost difference between conventional and green fuel transport.
Thank you, Junhao. And now I'm going to talk about the future forecasting. So look ahead, the future of marine alternative fuels will not be dominated by one single solution, but will happen in phases. So in the short to medium term, from 2025 to 2035, LNG and methanol will act as bridge fuels since they can use today's infrastructures, and green methanol made from renewable energy is expected to grow quickly. Companies like Musk and MSC CGM are already investing in methanol fuel fleets, and hydrogen will be used mainly in ferries and short sea shippings where range requirements are smaller. In the long term, from 2035 to 2050 and beyond, ammonia and hydrogen are likely to become the main fuels for deep sea shippings once the issues like infrastructures, safety, and high costs are solved. In the industry is moving towards green corridors, trade routes where zero emission fuels will be also prioritized. Stronger international rules such as the IMO 2050 targets, EU ETS, and Fuel EU maritimes will speed up the shift. To conclude, these articles gives us a clear roadmap for moving away from heavy fuel oil. It shows that it's not perfect fuel, but together these fuels create a pathway to meet the IMO 2050 target. LNG and methanol are the short-term answers, while hydrogen and ammonia hold the long-term keys. So the journey will need technology innovations, global cooperations, and strong regulations. And finally, Decarbonizing shipping is not just a fuel choice, it is a shared responsibilities that will shape the futures for global trade. Thank you.
These are our reference. These are our reference. These are our reference. Thank you.